Hi students, in this lecture I am going to discuss a sound. Let us see the first sentence given here. Sound is a longitudinal wave in a medium. Sound waves are essentially pressure waves. So first understand these two sentences. Okay, let us see here the explanation part. So we are saying sound is longitudinal wave. For example, sound is a propagating along x-axis. Just a minute. Right. Sound is propagating along, let us say, along x-axis. Okay. Now we know the meaning of longitudinal waves. So longitudinal waves, when sound propagating along x-axis, oscillations of particles of medium. So first assume all particles of air are not oscillate. They were stationary initially. Assume that initially particles of medium not vibrating, not oscillating, they were at rest. Now sound is entering into medium, and we all know that sound is a form of energy. So when energy enters into medium, particles of that medium start vibrating. Particles of that medium start vibrating. Okay. Now it is a longitudinal wave. That means particles vibrate. They vibrate to and fro like this. They oscillate parallel to propagation direction. Energy propagates along x-axis. They oscillate along x-axis only. So when points are oscillating like this away from each other, next moving towards each other, right? So when they oscillate along propagation direction, we have compression and rarefaction. I am repeating. Since the particles vibrate along propagation direction, they compress. We have compressions and rarefactions. When particles come closer, when particles come closer in that region, pressure will be more than that of atmosphere. So initially, when there was no sound, pressure of medium was that of atmosphere. Now sound is propagating. So when particles are compressed, when they come closer in that medium, pressure will be more than that of atmosphere. And when they move away from each other, particles, that region becomes rarefaction. That means in that region, pressure will be less than that of atmosphere. So here if you observe carefully, when particles come closer, pressure is increasing. When they are moving away from each other, pressure is decreasing. That means because of longitudinal waves, in the medium, pressure changes from point to point. I am repeating. Because of longitudinal waves, pressure changes from point to point in the medium. And these pressure changes are responsible for sound. So our eardrums are responding for these pressure variations. Or if you are taking a microphone, that responds to these pressure changes. That means pressure variations are responsible for sound. That's why sound is called a longitudinal wave. Sound is called a longitudinal wave. That is what we can see here in first sentence. Sound is a longitudinal wave. Because of this longitudinal wave, pressure is changing. And if you see second sentence, they are essentially pressure waves. The reason is that Pressure variations are responsible for sound. That's why sound waves are pressure waves. Okay. Now sounds having different frequencies and we cannot hear all frequencies. So for human beings, the frequencies are 20 to 20 kilohertz. Only these frequencies we can hear. This is what we call audible range. So for human beings, 20 hertz to 20 kilohertz. This is what we call audible range. So frequencies above, frequencies below, we cannot hear, right? So frequencies greater than 20 kilohertz are called ultrasonics. So example is sounds produced by bats. And frequencies less than 20 Hz are called infrasonics. And example is seismic waves, right? Now focus relation between displacement amplitude and pressure amplitude. See what is it? So till now we have taken representation of a wave. It is like y equal to a sine omega t minus kx, right? So when we have taken transverse waves, we have taken y equal to a sine omega t minus kx. So this equation represents a plane progressive harmonic wave. And from this, what we can say is energy propagating along x-axis and oscillations are along y-axis, right? But coming to here, it is longitudinal wave. If energy propagates along x-axis, oscillations also along x-axis. But to avoid confusion, instead of writing here x, we are writing as y. But we have to keep in mind y is displacement of those air particles along x-axis. I am repeating. Here y stands for displacement of the particles of medium along the propagation direction. That is now here along x-axis, right? But coming to sound waves, they are because of pressure variations. That's why we prefer to represent with the help of pressure variations. So I am writing here change in pressure. Change in pressure is equal to maximum change in pressure delta P naught cos omega t minus kx. Okay. So here onwards, we are going to represent longitudinal wave or sound waves with pressure variations instead of displacement. Okay. Right. Now we want to connect displacement amplitude and pressure amplitude. Okay. So how to connect now these two? Focus carefully. Let us consider, just let us consider, take a different photo for this. Yeah. Just imagine one cylinder in air medium. Imagine one cylinder. Consider a small part in that cylinder. Let us take a small part in that. We can say this is x coordinate and this is x plus delta x. Okay. So we have taken a cylinder, or you can say imagine a cylinder in that medium, and in that cylinder focus one small part of the cylinder, that is x plus dx. Okay. When there was no sound, pressure at this layer, pressure of atmosphere, And at this layer also, it is pressure of atmosphere. Okay. Or to avoid a confusion, take P suffix here, atmosphere, right? When sound propagates, what happens is, see carefully, when sound propagates, let us consider this layer moves by a distance y. Assume that this layer moves by distance y. And this front layer moves by a distance, it is y plus delta y. Okay. So this layer moves by y distance. This moves by distance y. And this layer moves by y plus delta y. Okay. Now see what we can write here. We know that bulk modulus equal to minus delta P by delta V by V, right? So from this we can write, delta P. Delta P means change in pressure, that is equal to minus B into, see, in the place of delta V, change in volume. Change in volume means, see, this layer moves by distance y, but this moved by y plus delta y. So what is now change in volume? If you take cross-section area as yes, change in volume will be, take first here delta V by V, that is equal to minus B into, in the place of delta V, S into delta Y. Okay. Because this is moving by y distance, but this is moving by y plus delta y. So change how much? It is S into delta y, right? I hope you are getting it. Right. Coming to initial volume. Initial volume, S into initial length equal to delta x. Okay. So now this will be minus B into delta y by delta x. Okay. Right. Now, if you consider delta x is very small, then delta y by delta x becomes dou y by dou x. This is if delta x tends to 0, means very small. Okay. This is one important result which you have to remember for solving problems. Right. So this result you have to remember for solving problems. Okay. Right. Now we want relation between displacement amplitude and pressure amplitude. Right. Now see what we can do. First find here dou y by dou x. Okay. So I'm writing here delta P equal to minus B. See what is now derivative of y with respect to x? With respect to x. Minus AK cos omega t minus kx, right? That is equal to abk into cos omega t minus kx. That is now delta p. Now that is equal to delta p naught into cos omega t minus kx. That means, see what we got, delta p naught now. Delta p naught is now, it is delta P naught. I am writing here delta P naught equal to, it is ABK. Okay. So this result also we have to keep in mind for solving problems. I can say this is equation 1, keep in mind, very important. And delta P naught A, B, K is also very important for solving problems. That is now relation between pressure amplitude and displacement amplitude. Okay, right. Now you can see for this notes, we can see here neatly that initial volume. Okay, initial volume S into delta X, change is S into delta Y. Then we have taken bulk modulus, and then we got result is delta P equal to minus B into dou Y by dou X. Condition is delta X tends to 0, means this is very small, right? This is what we have discussed, right? Okay. Now see, we have taken Y equal to A and omega t minus kx, finding slope, and finally we got delta P not equal to ABK. Now see carefully here. Now see carefully. This is YX graph. YX graph, right? So YX graph, what I'm doing here, I'm writing this graph for t equal to 0. I'm repeating, this graph is when t equal to 0. When t equal to 0, y equal to sine minus kx. Okay, this graph is when t equal to 0. So when t equal to 0, y is sine minus kx. So it is now minus sine graph. So minus sign means it is graph is like this, right? Now see carefully, coming to pressure, delta P equal to, see what we are writing here. In the previous one we got delta P equal to minus B into slope, right? Minus B into slope. Now see this one, slope is minus AK into cos function, right? Okay. Then see what we are getting here. Delta P as a function of x. Take t0 here. We are saying this is a graph when t equal to 0. So t0, this is a cos minus omega t. And we are knowing that cos theta equal to minus cos theta is also equal to cos of minus theta, right? So cos of minus kx is equal to cos kx, right? Then see what happens. At this point, when x equal to 0, cos value 0 means delta p equal to delta p naught. It is maximum value. So this is maximum. Okay, this is maximum. And if you see carefully, at point A, slope is negative. Slope is negative. Or you can say at point A, slope is minimum. I am repeating, at point A, slope is minimum, right? When slope is minimum, we can see in that equation, when slope dou y by dou x is minimum, right? We got here dou y by dou x is negative, negative of negative positive, right? That means now delta p is maximum. Delta p is maximum. We can see delta p maximum, right? Slope is minimum, delta p max. And if you see carefully at this point, slope is 0. Slope 0 means there is no pressure change. So delta P 0. So at this point, if they ask what is the pressure, it is pressure of the atmosphere. Okay, right. And if you see carefully at point B, slope is maximum. When slope is maximum, delta P is minimum, right? Or you can say change. Okay, delta P is now how much? Minus delta P naught. If question is asked like at B, what is the pressure? At point B, what is the pressure? It is pressure of atmosphere minus delta P naught. Okay, because change is minus delta P naught. So at point B, pressure is equal to pressure of atmosphere minus delta P naught. Okay. At A, if they ask at point A, pressure of atmosphere plus delta P naught. Remember at A, pressure is maximum. That is a compression point. I am repeating. At point A, pressure is maximum. That is pressure of atmosphere plus delta P naught. That is known as a compression point. So here points are moving towards each other like this. Towards each other like this. Okay. Compression point. Coming to B, rarefaction point. So here points will move left of B, left side, right of B, right side. Okay, that is rarefaction point. At A, what happens? Left of A moving right side, right of A moving left side. So this is now compression point, maximum pressure. B corresponds to rarefaction point, minimum pressure. Like this, we can expect questions basing on the result minus B into slope. Okay, right. Now see next one. How to calculate speed of a sound. How to calculate speed of sound. Okay. Yeah, you can see diagram here. We have taken same diagram as previous one. Taking imagine one cylinder, length is delta x, pressures P naught when there was no sound propagation. Initially assume that there was no sound. Assume all particles of medium, they were at rest. Now, once the sound enters into medium, they start oscillating. Okay. Now, the front layer, this layer is moving by distance y, and this moves by y plus delta y. Okay. I will make calculation here. Right. You can see here the same diagram we are taking. This layer has moved by a distance y, and coming to this front layer has moved by distance, it is y plus delta y, right? So pressure here, it is now pressure of atmosphere plus delta P1, and here pressure of atmosphere plus delta P2, right? If you assume that delta P1 is greater than delta P2, the net force will be, I will write here, net force will be delta P1 minus delta P2 into surface cross-section area. Yes. This is net force. Net force equal to mass into acceleration. See, mass equal to mass of that element equal to, what I can do here is, it is now element of length delta x, right? So it is now rho into S into delta x. That is now giving us mass of that element. This is rho. S into delta x. S is the cross-section area of the cylinder. That area into length of cylinder gives volume. Volume into density gives mass. That is mass. Mass into acceleration. Acceleration, I can write it as dou square y by dou t square. Okay. Now see, this is taken as delta P. Delta P equal to rho into delta x into dou square y by dou t square. Right. Now this can be written as dou P by dou x. That is equal to rho into dou square y by dou t square. Okay. And I am taking here negative sign. And see why I am taking negative sign. Since we have taken delta P1 is greater than delta P2, net force is along positive x-axis. Positive x. And along x-axis, pressure is now decreasing. I am repeating. Along x-axis, pressure is decreasing because delta P1 is greater than delta P2. That's why derivative of pressure with respect to x becomes negative. Negative of negative positive. Okay, right. Now we want to get what is the value of dou p by dou x. Let us call this as equation 1. Okay, right. Now focus the result earlier what we got. Okay, earlier what we got result I am writing here. We got delta p equal to minus b into dou y by dou x, right? We want dou p by dou x. So differentiate now this result. Let us take this is a 2. Differentiate now 2. Then dou p by dou x is equal to minus b into dou square y by dou x square, derivative of a slope. Now use this result in equation 1. Okay. Then see what we get. So putting this one in equation 1, this becomes now, or I can write rho into dou square y by dou t square is equal to, placing this there, it becomes b into dou square y by dou x square, right? Writing this as dou square y by dou t square is equal to b by rho into dou square y by dou x square. Now compare this equation with wave equation. Compare this equation with wave equation. Okay. And see what is wave equation. It is dou square y by dou t square is equal to v square into dou square y by dou x square, right? And this is wave equation. So when we compare this equation, what we got, and with wave equation, in the place of v square, we have b by rho. Okay. So I am writing here. Let us take different color. Right. So comparing those two, we are getting v equal to root of b by rho. This is our expression for speed of sound in fluids. Okay. Suppose if you want to write same thing for solids, then what we are doing is writing this as in general v equal to root of E by rho. E is known as modulus of elasticity for solids. For solids, we are writing this as in the place of E, it is Young's modulus. And if you want for fluids means it is gases as well as liquids. For fluids, in the place of E, we write bulk modulus. Okay. So general expression is speed of sound equal to root of E by rho. Okay. E is known as modulus of elasticity. If you take for solids, replace E with Young's modulus. For fluids, means gases and liquids. We write bulk modulus, right? That is now derivation for speed of sound. Okay, that is what you can see here, right? So net force on the element, this is what we have taken. Then slope here, and next we got here comparison. And after having comparison, this is a general one. What we got E is the modulus of elasticity. So you can take this notes, right? Okay. So for solids, E equal to E is Young's modulus, and for fluids, E is now bulk modulus. Okay, right.